it's settling. Okay, so this is our particle, and let me give it a little shade to it. Okay. And when this particle is in water, then it will undergo certain, or it will be experiencing certain forces. So what are the forces? So one force is uh, you know, force due to gravity, and then we have another force which is force due to buoyancy. Okay, so we have a force due to buoyancy, and also we have force due to drag, because this particle is moving inside water. And as you understand, the drag force is opposite to the direction of the motion. Okay. Okay, so drag force is opposite to the direction of the motion. Now, when we, just to give you a practical example of a drag force, if you are going on a highway and riding a bike, you can understand that uh, the air is pushing you behind the opposite direction of a flow, and the more you accelerate, the more is your speed, the more is the force of the opposing force that you experience in this case. So drag force is you know is in the opposite direction, is in the opposite direction of motion. Okay, and just to write down the forces, force of buoyancy is nothing but rho W. V is the volume of the particle, and dP into G, right? And force of gravity is nothing but mass into volume, sorry, density into volume into gravity. So if this is okay, and when we talk about the force due to drag, so drag force is given as force of drag equals to half of the density of the medium through which it is going, so rho W, and then we have coefficient of drag, which is CD, and then projected area of the particle, and then velocity of the particle. Okay, so so this is coefficient of drag, or drag coefficient. Okay, and then you have rho W. So this is projected area of the particle, projected area of particle. Okay, and here we are considering circular particle, and V is the velocity. All right. So now what happens is that initially think about there is no force of drag. So force of gravity and force of buoyancy. Suppose this force of gravity is much more than the force of buoyancy, so the particle tends to settle inside the water. Okay, and as it so there is a net force acting on it. But if there is a net force acting on it, then there should be an acceleration, because we understand that resultant force equals to mass into acceleration. Okay, so what happens is that as the acceleration is produced, then obviously the V is going to increase. So acceleration causes V to increase, right? So as the V increases, then the force of drag also increases. So you can understand that the more is the velocity for the particle, the more is the opposing force to the particle. So at a certain point of time, the situation arrives that all the forces come in equilibrium. Okay, so if we try to write the resultant force here, the resultant force is nothing but force of gravity minus force of buoyancy minus force of drag. But these two forces are, force of gravity and buoyancy are, uh, they are kind of, it's not changing, but this force of drag is changing because velocity is changing. So at a particular time, they come in equilibrium. So we can say that, force, so this is like a, constant. Okay, so there is no resultant force acting on it. So that means you can see that acceleration becomes equal to 0. And if acceleration is equal to 0, that means acceleration is nothing but dv dt equals to acceleration, and this is equal to 0. So that means v actually is a constant at that particular condition. V becomes constant. So that means ideally the particle should accelerate for a very short duration of time, and until it occurs until the forces are become in equilibrium, causing the force of drag to be there, playing a very important role. So V becomes a constant, and this is known as Vt, or terminal velocity. So when a particle tries to uh, settle in a media which is creating lot of shear forces, or a viscous media, then obviously the velocity becomes equal to a constant velocity after a certain amount of time, and this is known as terminal velocity. Okay, so as we understand that when the terminal velocity is achieved, then the resultant force equal to 0. So that gives me Fg equals to Fb plus Ft. Okay, and now put in the numbers here. So this is rho s Vp into G, and this is rho W Vp into G. By half of Ct rho W Ap, right? And so this is what you get, and you can write as 2 rho s minus rho W Ap G divided by Cd rho W into Ap. Now plugging the values Vp and Ap from here, and that's what you get is, you can see here, what we get is nothing but, so you have 2 here, and then rho s minus rho W, and Vp is 4 by 3 by R cubed. Okay, and you have G here, and this is Cd rho W into pi r square. So what you get is 4 by 3 rho S minus rho W uh, by rho W, okay, and then I write this as G by CT into rho R, right? And so this is the root over, okay, and this comes into 4 because this is V square, right? And then 2R equals to D. So if D is the diameter of the particle, so you can write 4 by 3 G D by CT rho S, sorry, rho S minus rho W by rho W. So this is what you get, okay. So this is the terminal velocity of the particle that you get. So I'll write Vt here, okay. And so now we have to understand what is CD, okay. So CD is the coefficient of drag, and when we talk about the coefficient of drag, so let me have a new slide here. So CD is the, so let us see. So we do not know the value of CD. Let's do it here only. Okay. Alright, so what is CD? CD is coefficient of drag, and this is a function of Reynolds number. So we all know. So this is RE is Reynolds number, and Reynolds number is given by rho W V into D by here. Okay. So here the velocity is the terminal velocity, right? Vt. Okay. And so Ct is not a constant; it varies with respect to Reynolds number, and so Reynolds number is given by this value. But when Reynolds number is less than 1, or when it is laminar, we write Ct equals to 24 by Re. Okay, and when Reynolds number is between 1 and 10 to the power 4, so this is known as terminal zone, and Reynolds number greater than 10 to the power 4, so this is known as turbulent zone. And when we are in turbulent zone, then we Ct equals to 0.4, and in between, which is we know as a zone of transition, so we can write Re plus 3 over root over Re plus 0.4. So this is what we get for the values of Ct. Yes. Now, when we have these values of Ct here, then of course we can bring in other values. So let us see what happens during terminal. So we can see this is our equation. So what happens in terminal zone? Laminar zone, Ct equals to 24 by Re. So let me write down in this expression what is the value if we put this here. So let me write from here. So as you can see, Vt square equals to we have 2 into rho S Vt square equals to okay, so you have 2 into rho S minus rho W divided by, and you have G, you have Vp, and then you have Ct, Ap, and rho W. Okay, and here you can write down, so you have 2 into rho S minus rho W G into 4 by 3 by R cube divided by CD is 24 by RE, okay, and you have pi R square into rho W, right? So if you now put the value of R equals to, you can see R equals to rho W VT by mu. So R equals to rho W VT by mu is the viscosity of water. So you can plug in the numbers here, and now you can get 2 into rho S minus rho W into G, and this will be 4 by 3, and you have R here, okay. Now you have 24 and RE comes up, so you have, in place of RE you can write rho W VT E by mu, okay, and we have rho W here. So now if you do a little math, what you get is the value of Vt will be G into rho S minus rho W. So rho S minus rho W, okay, divided by 18 mu, okay, into d square, okay, and this is known as Stokes law. So this is known as Stokes law. So this is a very famous equation, and when we deal with sedimentation, normally we try to find out a Stokes law region, and if this is not in a Stokes law region, then we have to go for finding out CT value from this terminal zone or whatever. Okay. So now normally we find out that we deal with particles which smaller diaparticles which is in the Stokes law region. So how we find it out? So when you have to find out the terminal velocity of the particle of size, let's say d, then first of all you think that this is following a Stokes law principle, or this is in laminar zone. So when you put this value, you'll get some value of Vt, and then when you get the value of Vt, find out the RE corresponding to it. So you have rho W, you now know Vt, you know the value of d, and you know value of mu. So you can find out the value of RE and check whether where does RE lie. Okay. So if RE lies in, if RE is less than 1, then you're fine. You can say that, well, my assumption is correct because it is in laminar zone, so the value of Vt is what we have found out. But if it is not, and if you find this is in transition zone, then you have to follow some iterative procedures. How this iteration will go on. See here, please find out the value of Ct from here. Putting this value of Re that you have gotten. Okay, so you have whatever value of Re that you have gotten, you put this in here and find out the value of Ct, and then put this value of Ct in this equation and find a new value of Vt. Okay, and then when you find out this value of Vt, find out Re again from here and find out Cd, and now put this value here again in this equation and try to see the new value of Vt. So the values of Vt will now converge to a value, and when you see that there is not a significant difference between two iterations, successive two iterations, then you understand that you have found out the correct Vt value. Okay, but this is not a part of so you might have known this for a long your BTech days, so I'm not trying to get into this again. Of course, maybe I'll, uh, you know, probably in a tutorial class I'll discuss this. But right now I don't want to get into this. Okay, so this is what we have found out a terminal velocity is, and terminal velocity, as we have seen, is the velocity with which a particle will settle down when it is allowed to settle in water. Now, when you talk about sedimentation, sedimentation is all about settling. Okay, so sedimentation is all about settling, and as you might know that we have four types of sedimentation. One is called type 1 sedimentation, and then we have type 2 sedimentation. Okay, we have type 3, and we have type 4 as well. So I'll just give you a brief, about what are these four types of sedimentation. I know those who have been in my wastewater engineering course earlier, for BTech students, you already know about this. So just take it as a recap for you. Okay. So here, if you put suspension of, let's say, first let me, because this is more or less seen in wastewater, all these four will be seen in wastewater engineering. So let me give you an example from wastewater engineering. Suppose you have a solution taken from a wastewater treatment plant, an activated sludge process, and put this water in a measuring cylinder. Okay, and what is this measuring cylinder? You have the bottom is, it is not an infinitely long cylinder. It has got a finite end where all the particles, if it touches the bottom, it comes to the rest. Okay, so for the purpose of this course, we will consider that as any particle touches a surface, it comes to the rest, by touching that surface. Okay, now if we take particles from wastewater treatment plant, mainly activated sludge process, you see there will be particles like agglomerated or individual particles of bacteria. They will be suspended in water. So initially, what will happen that you will find a more or less homogeneous solution with particles uniformly dispersed within the cylinder. Okay. Now, if you let this thing to stand for some time, what will you see that the particles will start settling down. The particles will, with their respective terminal velocities, they will start settling down. Okay, and initially the settling will be discrete settling, because all the particles will tend to settle by its own, but there will be some particles which are at the so this happens is that if you come back after, let's say, an hour or so, or maybe 2 hours or so, what you are gonna see is that at the bottom of your cylinder you have got some depositions. Okay, you have got some depositions right here, at the bottom, and this zone is actually, as the time progresses, the you know the zone which is at the bottom, they are growing over time. And what happens at the top? You start seeing a clear solution from the top. Okay, and then as you look at the solution here, probably the thick the solution will go thicker and thicker as you go at the bottom. So this is what normally we see during the settling. So what happens is that initially there are initially there will be discrete particles settling. Okay, so the particles settles by themselves. So this discrete, so we call it discrete particle settling. And then when they are settling each other, and because this is a wastewater solution, there will be a lot of polymers, and you will see polymers secreted by the bacteria themselves. So they will tend to agglomerate with each other as the time will progress, and when they agglomerate, so the particles will come closer and agglomerate by maybe polymeric action or otherwise, and they will grow in a larger size particle. So if they grow in larger size particles, you can see that the value of d increases and the terminal velocity increases. So as it grows bigger and bigger, its velocity increases. It doesn't remain same throughout the throughout its journey. Okay, but again, when you talk about discrete particles which do not agglomerate, their velocity remains constant. But for those who agglomerate, their velocity changes as the time passes. So we call it agglomerated settling, or which is known as type 2 settling. Okay, and then we have a type 3 settling, which is nothing but, you can see there will be a zone here where there will be velocity is a function of the concentration of this zone. Okay, so there will be and they actually settle like a blanket or a zone. The whole thing settles very slowly at the bottom. So this is known as zone settling, or so this is known as zone settling. Okay, and here the terminal velocity, I mean the velocity of the settling, is a function of concentration of the solution. And then lastly we have type 4 settling, which is known as compression settling, and this is not really settling, but as because it is also a part of settling phenomenon in the cylinder, this is known as compression settling. So here you can see that when the particles sit at the bottom, suppose there is a particle settling at the bottom, and then another layer of particles tries to sit on top of it, and as because the weight or pressure is increasing over these particles, the water that is retained within the particles, they will get squeezed out and they will try to come out from here. Okay, and this zone actually gets compressed due to its own weight. So we call it a compression zone, or so here the compression or the settling or the displacement of the particle takes place because of the water gets squeezed out from this particular zone, and this is why it is called a compression settling. Okay, so these are the 4 types of settling that we can see around us. But for water treatment, normally we talk about discrete particle settling, and agglomerated settling is occurring when you have added flocculators or flocculators or coagulators in coagulating chemicals in water. So if we try to draw a curve here about suppose you have you're trying to plot a curve about the distance traveled by the particle distance traveled by the particle with respect to time. So if it is the height of the particle from the top, that's right here. Uh, you know, so, and this is time. So, this height is, let's say, it's not like this. So if we find out height from here, okay, height of the particle. So we started from this height, right? And then as the time progresses, and there will be the height diminishes. So this particle comes down as the height diminishes, right? And as the time progresses, the height diminishes, and so it will be a curve which is falling down like this. But what will be the nature of this curve? As you can see, the velocity, terminal velocity is a constant, as long as this is discrete particle setting. So if this is a constant velocity, h by t, or gradient of the line, is what? Is the velocity, right? So h by t will be a constant value. So you get a straight line, which represents the type 1 setting. Okay. So you get a straight line which is a type 1 setting, because velocity is nothing but the distance traveled, distance over time, and so here the velocity is constant, so it will actually have a same distance at the same interval of time, so you get a type 1 settling. Now if we talk about agglomerative settling, because the velocity will increase as the time progresses, then obviously you'll get a curve like this. So this will be a parabolic curve, because as the time progresses, the velocity increases, and this is what you get. And so this is a type 2 settling. I'm not going to talk about type 3 and type 4 here, because this is all the more concerned with wastewater engineering. So obviously we do not discriminate between wastewater and water in this course, but that might be out of the habit. Okay, so let's talk about yes.
Sir, we are assuming that the particles are at terminal velocity at t is equal to 0.
Terminal velocity v equal to 0.
No, sir. At time t is equal to 0, they are at terminal velocity, right?
At the time t equal to 0, they are at the top. Yes.
And at that time they have attained the terminal velocity, like in the graph you plotted, you just made here. You have we started with terminal velocity, right?
I mean, yes. Initially there will be a little acceleration, very short period of time, so but which is maybe a fraction of a second. So if we allow it for settling for like 1 hour or 2 hours, then the initial acceleration won't be significant. So for rest of its journey, it will be a constant velocity fall, right? So that is why you can see that we have plotted this like a straight line.
That's why it's a linear curve. There is no
there is no change in the velocity during its time of fall. But when you talk about type 2, the velocity changes because the particle grows bigger and bigger. As you increase the value of d, the Vt is increasing. So here d goes on increasing, and this is like a square. Okay, so here the increase will be in like a parabolic increase in the velocity. So you can see here the time requirement is also, so it's kind of a parabolic curve which is coming from here. Okay.
Okay.
All right. So let's now very quickly get into our concepts of settling. Okay, so now let us say that we have a settling basin through which particles are settling, and if we see this is, let's say this is our settling basin. Obviously, a settling basin may be a circular basin as well, and but so I could have taken a circular basin in consideration, but for simplicity or the way you have been taught, let me think that we will just consider velocity which is in this tank to be a rectangular tank, settling tank. Okay, so the rectangular settling tanks, let's call it the width as B. Okay, so this is B is the width of the tank, and we have a length L of the tank, and we have a height, let's say, H of the tank. Okay. Okay, and let me have a long section, have a look at the long section of the tank, and this is the long section that we are looking at. Okay, so this is your length L, so I'm taking a long section, and this is L, and this is your height H. Okay, now when we define a particle, as you said, as you are seeing here, we consider that the particle has come to a rest, when the particle hits at the bottom. So that's when we consider that the particle has come to a rest and it will not get resuspended again, it will be just settling at the bottom. So here, if we understand that the particle has to settle, then it has to reach at the bottom. So at any point of any place, it has to reach at the bottom. Okay. So when the limiting case, when it does reach at the bottom, or limiting case of reaching at the bottom, occurs when it is here. Okay. So that means now for a particle which is introduced at the top of the settling basin, we will consider that it has got settled only when it reaches at the bottom, and if its velocity is constant, then we will see that this will be its trajectory, and this is how it will move. But consider, so how it is going to move, right? Now, all the particles which are having velocity greater than our terminal velocity, let's consider that, suppose this is our terminal velocity v0 or vt, and at the same time, because we are introducing water from here, from this side, and taking out water from this side. Okay, so taking out water from this side, so it's a continuous reactor. This is your flow going in, and this is your flow going out, and during this time the particle will settle down at the bottom of the tank. So during this time the particle is going to settle down at the bottom of the tank, and this is what we try to do in our settling basins. Okay, and so so as you can see that the particles will have a velocity towards the downward direction, but it is also going in this direction, so it will have a velocity in the horizontal direction as well. So we call it Vx. Okay, and this particle is considered to be just trapped in our treatment tank. Okay, so the time, let's say the volume is such that the time of detention within this tank is V by Q. So let us consider that volume of the tank is V, and the time of detention is V by Q. Now, what is the horizontal velocity? Vh is nothing but you have Q going in, and horizontal. So So you just consider a cross section from here. Your cross sectional area that we are talking about, right? So this is Q B by H, right? And now, so we can see that the particles which are just trapped, here, they will travel a distance L at this particular time TD, and you know while and they will have a horizontal distance traveled L during this time and a vertical distance H traveled during this time. Okay, so this is what it does, right? So we can say that time of detention will be such that the horizontal distance traveled within this time and vertical distance, what is the horizontal distance traveled L, and with the velocity vh, it will take t time to reach at the bottom, I mean to reach on the other side. And if you consider the height to be gained, drop is h by v0, right? So this two, for this particle which is just trapped, this will be the limiting condition. So if, and v0 is what? v0 is our Stokes law velocity. v0 is our Stokes law velocity, or maybe settling velocity. You can write settling velocity as well. Okay, so you can see from this discussion is that your v0. So this is this equality. Look at this equality, and you can find out that v0 is equal to vh into h by L. Okay, and what is vh is q by ph, right, from here. Okay, and this is your h by L, and this is your q by b into L. Okay, so this is what is b into L. So b into L, this is b, so this is your b. Okay, so this is your b and this is your L. So so this is your L. So this is, we call it surface area. So this is your surface area, so this is your surface area of the tank. And so you can see that it's kind of perplexing, but it is this is what it is. So your velocity, the particles with Stokes law terminal velocity of v0 will be tapped in this, will be just trapped in this settling basin, but this is actually is q by as, which is, so if we want to remove a particle with settling velocity v0 and with a flow rate of q, then provide as amount of surface area. So if we want to remove a particle of settling velocity v0 and for a flow rate q, provide a surface area of as for this. Okay, now what happens if I have particles which are larger, or so if we have larger particles, so for larger particles, d is higher, so your v0 is, V is higher than V0. So, so, so for those particles, yes, they will have a, trajectory like this. So all of them will be 100% retained by this, because they were going to surely, heat at the bottom. So, all particles. So if your P is greater than equal to V0, then so as long as your Vt is greater than V0, these particles are removed 100%. All right. So now, what happens when this is not the case? Let us try to see this case here. If your particle velocity is less than V0, so Vt, if Vt is not equal to V0, now what happens? If your Vt is less than V0. Okay. So let us see what happens for this particular cases. Now let us draw another figure here. Okay. Another figure here, and let us say that this is our limiting case. So this is our limiting case, and for this we have VH, and this is V0. Remember, VH is same for everyone, whether it is bigger or smaller particle. But for, now we are talking about, we are trying to find out a particle for which V0, Vt is less than V0. If Vt is less than V0, if Vt is greater than V0, the trajectories are going to be like this. All right, agreed? Okay. Now, if Vt is less than V0, then what is this trajectory is going to look like? Well, the trajectory is maybe going to look like this. So this is our VH, and this is our Vt, which is less than V0. Okay. And but how to find out how much of these particles will be will be retained? So in our definition, it is hitting the bottom, it is going to be retained. Now for this we have to consider this fact that as the water is getting into this section, the particles are distributed uniformly over the depth. Okay, so the particles are uniformly distributed over the depth. So if all the particles are uniformly distributed, at the beginning, okay, or at the inlet, okay, right, at the inlet. No. So if this happens at the inlet, then what we going to see? So all those particles which will, if this particle is here, and here and here, so they will have the same, same slope, right? They will follow the same, or if I write parallel lines with this one, if I draw parallel lines with this one, they will have, follow the, this trajectory. So you can see that if I draw a parallel line, to this, which actually meets in here. So let me draw a parallel line from here, and it actually is here. So then you can see that the particle which is introduced at a depth, let's say small h and below, they will be all trapped. But the particles which are between this and this, so these are not going to be trapped, so they are not trapped. But the particles which are introduced at a height h or below, they will all be trapped, right? So for for all the particles entering at depth or height, let's write height, at a height h or below, okay, below, they are all trapped, okay. So we can say that h over h is actually Vt over V0, okay. And so for, if we try to find out fractional removal, if R is the fractional removal of these particles, so this is fractional removal of these particles, if, so that is h over h, and this is nothing but equals to Vt over V0. All right. For all the particles, so this is for only the particle which is having, like a transition velocity Vt. Let's write here Vt1, 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 and by V0. So if we try to find out, percentage removal of particles, all the particles, so this is nothing but 1 minus, let's write P0 plus sigma of all the Ri's, okay. So what is this P0? Just I'm writing, you now can understand. So P0 is the fraction of particles, particles having settling velocity equal or less than v. Okay. So this fraction is not totally removed. It's having velocity. Not less, right? Less. Okay. Less than. Sorry about this. So these particles gets doesn't get totally removed, but what is 1 minus P0? 1 minus P0 is the fraction of particles having settling velocity greater than V0 or equal to V0. So they will all be removed, that we have understood. So this will be all removed, but for this a fraction will be removed. So we can also write this as, if we can have a continuous function here, we can also write this as 1 over V0, and then you can write, so this is, you can see Vt by V0. So, let me write like this so that you understand straight away. Sorry about this. Okay. So this is nothing but equals to 0 to V0, and then you have Vt, let us write V by V0, okay, Vt is by V0, okay, and then you have Vp. So you can write this as 1 minus V0 plus, V0 is a constant, so V0 and 0 to V0, Vt into T. Okay, so this is how we can find out total percentage removal from this basin, and I will give you certain tutorial work to do, so from where you can learn it much better. Okay, so that's it for now today. So I wish to have another class. So far we have been doing 3 classes a week, but we have another class as designated as a tutorial class, which I think we need to do. Okay, so if you are okay to do it from today, we can start it today, and the time is from 2 to 3. So I can meet you at 2 to 3 But if you are not willing to do it today, then we can start from the next week. So if I can know your uh, opinion, that would be great. So if any opinion from you, can we do it from today?
सर हम लोगों की
Sir,
टुडे क्लास है आज 2 से 3।
huh? You have a class. Which group you belong to?
हेलो सर अर्बन सस्टेनेबिलिटी
Huh? Which group do you
हेलो
belong?
सर कोर्स 563 अमित अग्रवाल सर की ट्यूटोरियल क्लास रहती है यूजी की 2 to 3।
563 में आप हो?
ये सर
So please let me know when we can have a combined tutorial class because आपका जो tutorial class है मेरे साथ वो कब है?
सर हम लोगों का ट्यूटोरियल क्लास कल हो सकता है कल क्योंकि स्लॉट खाली रहता है 2 से 3 ट्यूसडे वाला।
Tuesday 2 to 3 is your slot open.
Yes, sir.
So the MTech students, do you have your slot open during that time?
No, sir.
What is that time?
Sir, it will be best if we can have on the allotted time on Thursday. I think we have a tutorial on Tuesday 2 to 3.
So okay. So can we all shift to Wednesday 4 to 5? Do you have anything on Wednesday 4 to 5?
नो सर।
I think nobody should have anything on Wednesday 4 to 5.
यस सर।
Okay. So let us shift our tutorial class so that everybody can join. See, I don't want to have 2 or 3 tutorial classes separately. So everybody should join between 4 to 5. Let's meet on Wednesday tutorial class from 4 to 5. Okay?
सर टीम में एडेड नहीं है हम लोग।
टीम कौन है टीम में एडेड? आप नहीं हो?
नो सर।
आप मेरे को एक ईमेल भेजो।
यस।
क्या नाम है आपका?
जितेंद्र कुमार।
अच्छा, you send me an email. I will. But so then how could you enter? ऐसे हो गया?
सर बाई लिंक व्हिच यू सेंड रेगुलरली।
Sir, I'm
अच्छा,
not.
but you are not added on the team. See if you check your email. अच्छा ठीक है, मैं आपको ऐड कर दूँगा, जितेंद्र। Okay, I'll do that.
ओके सर।
Sir, I'm also not added.
I am also not added.
So those who have not been added, just send me an email. I will add all of you to the teams. Otherwise, I have sent, if you talk with your friends, I have sent at least 2 times, the link to join the group. So you can use that link again for joining.
सर हम लोगों ने लेक्चर 5 या 6 से मेल रिसीव करना शुरू किया है, उसके पहले के मेल हमें नहीं मिले।
नहीं, it should be everybody should get emails. ऐसा नहीं हो सकता है। But anyway, मैं तो रिकॉर्डिंग नहीं करता हूँ, so what you can do, I will upload continuously upload those things. You can just go over and have a look at whatever has been taught. ठीक है? Okay, Shahid Tanwar, did you have any question?
No, sir. I'm not in the team. I'm just saying that.
Okay, ठीक है, मेरे को ईमेल करो, मैं आपको वो कर दूंगा, या तो one of you will get No, or maybe I will send CEN 421 and CEN 502 में दोबारा मैं again I will send the link to join, so you can join. Okay.
Okay.
All right.
Okay.
So if you don't have any further questions, then let us stop here, and we will see you on Wednesday again. All right. So bye bye.